All right. So welcome to the continuation of the thermal sensors chapter today. We have started by outlining some physical background of thermal sensing, and we have been right in the middle of radiative heat transfer, where I introduced the law of Stefan Boltzmann. With the important constant, Stefan Boltzmann's constant. That's again a constant that's very easy to remember. In SI units, it just uses the numbers 5, 6, 7, 8. Yeah, so you can remember that. Now, to the minus 8, maybe that's one thing to remember, but I think apart from that, it's quite easy. The units can be remembered also when one knows what comes out, namely watt, and that it's multiplied by T to the 4. And so that is deeply rooted in thermodynamics, the thermodynamics of interaction of matter and electromagnetic radiation, and in the fact that electromagnetic radiation is quantized. Planck designed his law according to observations, and I'm saying designed because he had to interpolate two limit cases at small and large frequencies, and then well, he found a formula, and then he had to think about how he could justify that formula, and then he was able to say, well, if energy is not continuously distributed across all energies, but if the electromagnetic modes are charged in units of some quanta, that have an energy that is h bar omega or h nu. In his case, of course, it was some constant h, that was multiplied by the frequency, and later it was called Planck's constant. Well, then he was able to justify that, and that really kick-started quantum mechanics as one of the phenomena. And so we have this emission from a black body, from a body, the ideal emitter at temperature T. And such an ideal emitter is easy to construct. Now I'm saying here it's the surface of a body. And the ideal emitter actually is the surface of a body, of a very special kind of a body. What one does is actually one constructs a box, and then let's say this is insulated, but inside it has the temperature T. So the inside is at temperature T, and therefore the walls inside radiate into the volume of the box, the inner volume of the box. And then we can have this little hole at the surface, and what we observe emitted from that surface, coming of course originally from all those side elements, is equal to the black body radiation spectrum. So the black body is actually a black void, some say, and it's not so unnatural because I mean we're talking about the equilibrium of electromagnetic radiation with a temperature bath, and that's ideally realized by a closed system, which is then observed through this little tiny hole. We could also measure inside the box and see what impinges on the surface or what is emitted from a surface. You would get the same result. And that is the black body. And then we have this epsilon, which says that real surfaces of bodies don't emit like a black body. They emit less, with epsilon somewhat below 1. So they emit less, but as we will see, they also absorb less. A black body absorbs everything. This hole, if you let radiation come on top, it swallows it all. So it has the ideal absorption, but the surface can, of course, also reflect. And then the absorbed part of the radiation is not 100%. It's only a fraction, and that is an interesting aspect. So radiation is absorbed by bodies, and it's ideally absorbed by black bodies, and it's absorbed partly by so-called gray bodies. Gray bodies are those with epsilon smaller than 1. And what one has is that the absorptivity, and I should really write epsilon, replace epsilon by alpha. It is usually written by alpha. The absorptivity alpha or A is like epsilon, smaller than 1 and larger than 0, and it's actually equal to the emissivity. That is needed for thermodynamic reasons. If it were not the case, we would construct a thermodynamic perpetuum mobile. We could transfer energy from a colder body to a warmer body and heat the warmer body even more. That would be fantastic. If ever you have an invention like that, tell me, then I will dismount it. Dismount it in the principal sense, because I don't believe it's possible to circumvent that second principle, the second law of thermodynamics. And so if we have a surface here and it is surrounded by an environment at temperature T0, the environment sends out radiation in all directions, and in particular onto that surface. And what this absorption law of Stefan Boltzmann says, that the amount of energy per second, the power absorbed by the body, is equal to epsilon, or alpha, times sigma Stefan Boltzmann times T0 to the 4th power. And since epsilon is equal to alpha, we can also write epsilon. So that is interesting. It means also that if a body at temperature T0 is surrounded by an environment at T0, it emits exactly the same amount as it receives from the environment. That's reasonable. If it was not the case, if this was not the case, it would maybe emit more than it receives, and then it would cool down. But what it cools down is, of course, excess energy that is transmitted to the environment, so the environment would heat up. So if both were at T0 at the beginning, they would have a discrepancy. And that can't be. And if it absorbs less than the environment sends in, no, if it emits less than what the environment sends onto it, then the opposite would happen. It would heat up, and that can't be. Bodies at the same temperature have to remain in equilibrium. And so thermal sensors, at least radiative thermal sensors, are based on the fact that if this temperature T is no longer T0, but T equals T0 plus some delta T, then this environment can send in more energy than what the body loses, but the body will always lose energy by radiation, by Stefan Boltzmann's law. It just receives more. So if you are out there in an environment of 37 degrees, you will emit radiation in a quantity given by Stefan Boltzmann's law. Let's say you are the ideal black body, okay, and then you can calculate how much this is, and maybe that's an easy exercise, just to think about how much energy you lose. But don't be worried, you don't have to eat as much as you lose, because the environment sends in an equal amount. So you remain at thermal equilibrium, and what you eat actually is spent in overheating, in motion, in thinking, in these kind of activities. But if two bodies are at different temperatures, of course there is a net radiation transfer. What is radiated minus what is absorbed, and that if the body is hotter now in the middle, it has temperature T4, then this T4 is larger than the T0 of the environment to the 4th power, and then you may have a difference. However, if the T is equal to T0 plus delta T with a small delta T, then we can expand this T to the 4 into T0 to the 4th power plus 4 times T0 to the 3rd power times delta T plus some other terms that are small to the square and small to the cube and small to the 4th power. That's just the expansion of this term to the fourth power. That gives the leading here, the two leading terms. And if I now subtract T0 to the fourth power, T minus T0 to the fourth power, this is what remains essentially, plus some minor corrections that are dots there. And so for small temperature differences, one has a net power transfer that is proportional to the temperature difference. That's very handy because very often we have differential equations that involve some unknown heat, change, temperature change. And if all those effects are linear, then possibly the differential equation is linear, and then we can get a solution. For instance, how fast does a thermal sensor react to a change of the input radiation? That is then fortunately calculatable, computable, thanks to the linearization. So this is a linearization, and the factor 4 in front here of the Stefan Boltzmann thing. This is what remains of the t to the fourth, and this is the factor of 4 that comes here. So it's easy to calculate, and I just did a calculation before just to see how much watt I emit per square meter to my environment if I'm 1 degree hotter than the environment, and I calculated it's about 6 watt. So if I'm warmer by 1 degree than the environment, naked environment, then we're exchanging then that's 6 watt per square meter. And I'm about 2 square meter or 1.5 square meters large, so I'm losing about 10 watt per degree temperature difference. And of course, if the environment is hotter than me, it starts to be the case today, then there is 6, 10, 20 watt coming in. And to get rid of those, okay. So that's how we get rid of some evaporation. And then you can also think, about these thin structures, these thin structures that we have also seen that are essential components of many thermal sensors by their fabrication, because they need to be insulated so that they can really transduce any energy changes, maximum the temperature change. Thin structures, then we have, of course, emission in 2 directions, and we can then have 2 surfaces emitting in 2 directions, and therefore there is a factor of 8 here. But one also has to think that O, the epsilon, can be thickness dependent, because the absorption length may be smaller than, maybe larger than the thickness of the structures, and then things get more complicated, and one has to do some really more advanced calculations. Then let me talk about convection. Convection is the transport of fluids under external forces. That is an important thing also in some sensors. Let's think about thermal flow sensors, where a mass flow to be measured goes over a surface and removes some heat. This is a principle that is well known in sensing. Heat transport in thermal structures by the forced convection, the driven flow. Forced convection means really driven flow. A flow is given in a pipe. You pump something through. And as opposed to free convection. As I'm standing here, warm air is being, in this room, warm air is being generated or heated. Air is heated up by my body, and this warmer air rises and then circulates around me. That is free convection. We will just have a look at that in a second. So this forced convection, of course, is related to solutions of the Navier-Stokes equation. This is the transport equation for viscous fluids, air or water, through some structures or over some structures, the wind over the houses, or a fluid to be measured through a pipe. And when you look at the Navier-Stokes equation, of course, you have this quite complicated equation with several terms that have their different prefactors, and the way to consider these complicated differential equations is to make them non-dimensional, to simplify them to the utmost. And that is done by introducing length scales, rescaling length, times, and so on. And then there remains one parameter, or sometimes two, that cannot be reduced away any by more tricks. And in the case of the Navier-Stokes equation, this is the Reynolds number, which says that if I have a characteristic flow velocity of a situation, and I have a characteristic length, for instance, a wing diameter, and then viscosity of a fluid, and if that combination of parameters gives a number, and I have another geometrically similar scaled variant in another fluid, and by some chance the number in that other situation, that other flow velocity times that other length times that divided by that other kinematic viscosity gives the same number, then the flow patterns in the two situations will be identical. If I know how to solve one problem, I know also how to solve the other problem. So microfluidics is not, apart from some effects that Professor Zengerle will tell you, like slip flow and so on, microfluidics is like macrofluidics. It just that apparently the viscosity appears just dramatically higher, but that's only because L is smaller, and so we would need a smaller viscosity to produce the same flow patterns at the same velocities, and the velocities are also smaller, so we would need dramatically smaller viscosities to have the same flow pattern as in the macroscopic. But if you say, oh, I'll consider a situation in the macroscopic regime with dramatically small flow velocity and in that length, I will have the same pattern as in this microscale situation. So that's very handy. And we're here concerned with heat transport. And if heat transport is added to the Navier-Stokes equation, more such dimensionless numbers, irreducible numbers appear. Some are listed here. Nusselt, Prandtl, Rayleigh, Kassoff. We'll just see the Rayleigh number in the next slide as being, or second next slide, as being an important thing in free convection. And so, for instance, just to tell you that things can be different, that let's say the Rayleigh number doesn't necessarily model thermal phenomena. Here is a simple example of a boundary condition, some hot sheet, half sheet. Actually, it starts here and then continues to infinity on the right hand side, but it has its starting point here, and there comes a flow that is homogeneous. Then the fact that there is this surface makes the flow go to zero. There is some shear flow on the surface. So the flow slides over the structure, but at the surface, the molecules transfer momentum, and then they're reflected with zero momentum and on average. And there's zero velocity right at the surface, but as you get away from the structure, actually you have the situation as in free space. So far out there, we don't even know that there is an object disturbing the flow. And that zone of disturbance has a characteristic shape, which the flow dynamicists have, of course, calculated. People like Prandtl and Reynolds and all the old guys, that's really 19th and 20th century science, the solution of these equations. And so there is this extension of this boundary layer that says, oh, here we have some inhomogeneity. The velocity boundary layer is indicated by this curve. But then if this plate is also hotter than the surrounding, so instead of being at T0 like the surrounding air, it's at temperature T1, then there's also thermal diffusion into that fluid. The temperature of the fluid will also change, and but that takes time. But since time is kind of pushed towards the right in this flow, a location here doesn't have the chance to feel that there is temperature, because if that heat diffuses out there, it's also transported at the same time, and then it doesn't reach that point. And so there is also a thermal boundary layer that extends differently, and that depends on other properties than the kinematic viscosity. There is the heat diffusivity that is important, and therefore it's something independent. And it could be larger or smaller, but then the velocity boundary layer, but it's definitely different, not fundamentally linked to to the other case. So let's see a case of free convection. I'm just looking out there, I see some free convection. Yeah, there are some examples of free convection out there. Nature is full of surprises, when you know how to look at it. I'll just show you. So what is free convection? Something which you are looking at also daily in your frying pan. So you have this bottom boundary condition at temperature T1, hotter than the upper boundary condition. This now looks like a box, and think of it as a box, maybe. So there are boundary conditions at T0, and then the bottom is T1. What happens, I really think will happen, is that the fluid in here is heated, so it expands, so it becomes lighter, so it rises, and then it is cooled again, and then it flows down. So you have a convective cell that arises naturally. And these convective cells you see when you put oil in the frying pan, and you watch the oil getting hotter and hotter, and the reflection of the light of your, I don't know, ventilation. You can see that some patterns evolve, and there are some regular pattern of little bulgings. These are convection cells. Heat is moved up from the middle of those cells to the outside, and then flows down again. And it's not in the center of the pan and then out there. It's little cells that are then forming a regular pattern, actually hexagonal pattern, because that seems to be more natural for them than square or triangular, hexagonal, and this phenomenon you also see in spring, like now when the air is pretty cold up there, and the bottom is heated strongly, T1 and T0, then air rises, and it does so, and then you see these little clouds scattered across the sky. Every little cloud, it's not by chance that it's there. It's formed by hot water air rising and then cooling down and then condensing. And then it's down again. And so, who knows about that? The guys who do gliding, these gliding planes. It's a sport. They are always looking for rising air, because when they don't go to the ground, they can keep gliding on and on and on and on, along the star line. You have this also. So people go along the star line. You are down to business. For hundreds of kilometers in some ideal cases. But it can also be here in the field. You look for a cloud, you circulate under that cloud, go down to the next one. Friend of mine, it's not my personal experience. So, and it's a question, does that happen also? If I have a micro sensor, okay, so heated here in the center, maybe a flow sensor or some thermal radiation sensor that is now heated by the incoming radiation, does that sensor lose its energy by forced convection, by free convection? If it did, it would reduce the sensitivity, because instead of generating temperature increase, well, part of the incoming energy would be lost by other phenomena. We already have radiation. We already have, so we have seen radiation losses we have seen conduction losses within the membrane. And if there is another efficient mechanism, then our sensitivity would be degraded maybe even more. So it's important to know whether this is important. And again, now we can give this object some characteristic length L. Like this is also some characteristic length L. And then there is gravity. There is the thermal expansion coefficient of the fluid that might produce that transport. There is its kinematic viscosity. There is the thermal diffusivity, the efficacy with which heat diffuses into the medium. That is given by kappa, the thermal conductivity, divided by the volumetric specific heat. And so there is this Rayleigh number that tells us, okay, if there is a temperature difference T1 minus T0 equals to delta T, and we have all these other quantities given, if the Rayleigh number is larger than some critical value, then we will have free convection. And below, there will be no free convection. We don't have these circulation patterns all the time. There needs to be a critical value of delta T between the bottom, the soil and the air. And if the air is colder and the sun is really shining strongly, then we may have a larger delta T. And the L is large, it's maybe a few hundred meters here. So if we now shrink this whole scenario to a micro volume around a micro sensor, the L is really small, the alpha is still air, nu and delta is still air. So we probably need tremendously large delta T's to start this instability. And as long as the Rayleigh number is too small, because delta T is too small for those large dimensions, then the temperature will remain layered. It will just be layer by layer by layer by layer, or some simple thermal profile, which essentially will also transfer heat but by conduction, not by motion, only by transfer by hot molecules to colder molecules in a static way. And that's something different. And so you find these phenomena under the name Bénard convection and Overbeck-Boussinesq instability. I'll ask you at the exam to spell this correctly, of course. Yes, don't worry. This is French, Overbeck-Boussinesq. And so this thermal transition from one pattern to another pattern is similar to what you know from Rayleigh, from the Reynolds number. You know that if in a situation the Reynolds number exceeds a critical value, the flow transits from laminar flow to turbulent flow, chaotic flow, whereas it is quite deterministic before. It is still deterministic later. It's deterministic chaos, but it's chaotic still. And so in this case, Reynolds also has some critical values. And if you know about microfluidics, you probably know more about it than I do. So in microsystems, free convection is often negligible because the Rayleigh number is proportional to L to the 3. And when I was a postdoc, we asked ourselves these questions. These newly developed gas flow sensors of Felix Meyer. And then, okay, is there free convection? And so, okay, let's test it. Heat it up, and let's measure the temperature. And then let's turn it over. That's the temperature. Then once the hotter surface is below the cooler environment, and here the hotter is above the cooler environment. Definitely the dynamics will be different. Hot air may want to rise, but where it's already hot is in top. So, and we didn't see any difference at all as a function of the time. So we experimentally concluded that free convection was not important in these sensors. And later we thought about it. Yeah, this is how you proceed as an experimentalist. You ask a question, you make an experiment, and you don't see something, or you see something surprising, and then you think. Yeah, the theorist works differently. He says, what phenomena, and I'll calculate everything, and I'll spend nights and weeks calculating difficult things, and then he comes with an answer, maybe. Yeah, so we were more of the pragmatic type here. No? Yes. Why not this direction? Well, if I say, okay, yeah, this direction is also okay. Yeah, and this direction is also okay. Characteristic means, kind of a representative length. It's not something, a number that is very precise to the last digit, 5-digit correct, It's, yeah, so vertical, yeah. Where is the top? Yeah. T0 is somewhere around here. Yeah? So let's say T0 is here. Yeah? So I could have said also, well, characteristic length is maybe this L. Yeah? Some distance between hot and cold. Yeah? But it's not something which is often easy to state which one. Yeah? Which length. Yeah? If I take Reynolds situation, I say, okay, here's a pipe. A classical example, a constriction in a pipe. And I send in a flow here, and then here maybe in the back it can be turbulent. So which L do I take here? Should I take this as L, or should I take this as L, or maybe half of it? So people will say, okay, I'll solve this equation, and then if I take this length, then at that Reynolds number, so and so, it will transit from laminar to turbulent. But if I take the other dimension, I'm not so far away from the first truth. So it needs to be specified, of course, but that's why I said when the Rayleigh number is proportional to some representative L to the Q. Proportionality here, then the numerical value I did not specify. So let's look at a temperature sensor, which is quite widespread, a CMOS temperature sensor, which was invented by Meijer and Heusing at Twente. It's based on diodes or bipolar transistors. It's connected in a particular way. The functional principle is based on the diode characteristic. So here you have the typical dependence of the current that flows through a diode if you apply a voltage V. So if the voltage V is 0, then we'll exponent of 0, that is 1 minus 1, no current. If I apply a forward bias voltage, positive voltage, and this exponential grows rapidly above 1, and then we have kind of an exponential dependence of the current on V. And if I go to negative voltages, then this exponent becomes 0, and we have minus 1 times IS. So at negative voltages, the current saturates at, let me just draw this, since we're not all electrical engineers. So this is the diode characteristic current as a function of V, and this asymptotic value is minus IS. The saturation current, as it's called. And here, for large enough voltages, it's just very closely approximated by an exponential curve of V. And that exponential curve depends on T, as you see here. So if I have one diode and a second diode that I operate at either different voltages, so actually this this can be switched around. You know, I can express this as V as a function of I. Yeah, so V as a function of I, yeah, is of the form shown here. KBT over Q times the logarithm of the I, logarithm of I divided by IS plus 1. So if I have two diodes that are driven by the same current, but have different saturation currents, or have the same saturation current and are driven by different currents, then the voltages across them is different. And then I make a little simplification. I just cross out the plus 1, because I through a diode can be much, much larger than the saturation current. This is a total, not an exaggeration, a sub-exaggeration. Yeah, it can be powers of 10 larger than IS, if Q is large enough. And so this ratio here is many powers of 10, much larger than plus 1. So I neglect the 1. What I can then do is that I can do the subtraction of the two voltages. I have a differential voltage, which is proportional KBT over Q. And then here, almost everything cancels except the factor 8. Logarithm minus logarithm makes the logarithm of the ratio of the arguments, and the only thing that remains is this factor 8. Now you wonder, where does the factor 8 come? It comes from a widespread design, where you see here an array of 3 by 3 diodes, transistors, but operated, let's say, essentially as diodes. You have 8 around and 1 in the center. And now the system is provided with a current, I Ptat, and this current goes through this one sensor, this central sensor, and so we obtain this 1 voltage, VB1. And then in the second phase, in this system design, the same current is sent through the 8 identical diodes. That is, each diode receives 1/8 of the current. So we are in this mode VB2, where each diode is charged with 1/8 of the current, and therefore the voltage across each diode is only VB2. But they are connected in parallel, so their common voltage is VB2. So by switching back and forth and measuring the difference of the voltages, we obtain exactly this value here. And this value is logarithm 8, something like, what is it, about 2, times KBT over Q. It's proportional to T. Beautifully proportional to T. It's a sensor that gives you the value of absolute temperature. Proportional to absolute temperature. That's what PT18 means. So there are many circuits that are based on this kind of ideas. You can also have circuits that provide a current proportional to absolute temperature. So that was quite fascinating, and it exploits the exponential characteristics of a diode. But the fact that there is KBT in there, a wonderful principle. So this was invented in the 80s, and here we have a design example of Mark Baumann, whose name you have already seen in another chapter. I had these PhD students who worked on many CMOS designs, stress sensors, and then at one point I told them, now you join forces and you make this super duper chip that can measure everything, all stresses, and also the temperature. And Mark Baumann designed this. Not an invention of his. It was just an application of some older ideas. And the fact that it is arranged like this has a deeper purpose. Sensors are never identical, or diodes are never identical. Yeah, so there may be a gradient of properties from left to right, or from top to bottom. Yeah, so maybe the left diodes may have slightly smaller IS than the right ones. And the middle ones maybe have the same, or in the other direction. And by having this arrangement, we are doing an average over a slope. And the average of a slope, an inclined slope, is equal to the value in the center. That's a common centroid approach of circuit design. It's just a manifestation of Taylor series and elimination of convolution of Taylor series. What is added on one side is subtracted on the other side, and so on in all directions. So let's talk about thermal radiation sensors, detectors. We have here an infrared image by from Wikipedia, but I mean, many focal planar arrays produce images like that. I also had a building physicist, analyze the heat losses from my house. He came with an infrared camera and said, here is your heat leak. You need to insulate here. Yeah? And then and that your house is not white, in infrared. It is hotter and it's colder. And hot bodies emit more energy than cold bodies. And if you can detect that energy, you know where they are hotter. And so these bodies that emit thermal radiation have typically thermal temperatures that are around the ambient. And so the question is, what kind of radiation do I emit? I mean, there is conduction through the air, but there is this radiative transfer. And what kind of radiation do I transmit? And well, I said it is Planck's law. So here we have this U as a function of, let me say wavelength, as a function of wavelength, and there is a maximum, lambda max. And now you can read that the maximum emitted by bodies at 300 Kelvin is in this area, or the range of relevant frequencies around this. There is a maximum, maybe 10 micrometers of wavelength. Visible radiation has what wavelength? Nanometers. Yeah. So zero. I'm writing it in micrometers now, so that we have the comparison. So this is visible, the visible spectrum. If a body emits at these wavelengths, do you know what temperature it has? If a black body emits maximally in this range, what temperature might it have? How many? 1,000. Okay. Other suggestions? Probably hotter. Yeah, that's definitely the right direction. I'll tell you 5,800 Kelvin. It's the sun. The sun has a black body radiation spectrum that peaks in the wavelength range in which we see. What a coincidence. Oh. Well, evolution made it happen that we would see where most energy is being, available for C. So that's the wonder of evolution. Our ancestors who only saw in the infrared or in the ultraviolet didn't survive because they bumped into other crevices and things. Those who saw in the visible world have survived. We are the result of that. Simplified picture of evolution reduced to the sense of vision. And there is a famous law, the Wien's displacement law, it is called, I think. It says that lambda max yeah, is proportional to, and now I need to state it correctly, 1 over T. Yeah? The hotter, the smaller lambda max. It scales with temperature easily. Yeah? So if the sun is 20 times hotter than us, its peak wavelength is 20 times smaller than ours. Since the sun emits at roughly 500 nanometers, we emit at roughly 10 micrometers. So easy. And so this property of warm bodies, I won't say hot bodies, to emit radiation is of course used in burglar alarms, in intruder, in room occupation, in detectors for opening doors when somebody comes. When I come to a door and wow, magically it opens, there is a detector up there that sees my heat radiation. And I said, oh, some hotter body came just along, ooh, my signal changed. I need to open the door. And then you are in the ICE, you walk to the door, nothing happens. Because you think there's a pressure sensor and nothing. And all kinds of things, and then you wiggle your hot hand closer to the detector, and then it opens. Because then you have a larger warm surface. Well, it's better to clap the hands first to make them warm. So this is Deutsche Bahn technology. Sometimes it works, and I'm glad this is recorded because I have been pissed off so many times by debacle Bahn. So there are several types of detectors: pyroelectric detectors, thermoelectric and bolometric detectors to detect this kind of thermal radiation. Pyroelectric detectors are based on ceramic materials. So this is very non-CMOS. There have been attempts to combine these ceramic materials with CMOS subsystems, but the processing of the ceramics requires very high temperatures, sintering at many hundreds of degrees. That is totally non-compatible with, incompatible with CMOS technology. So this is a world apart, and companies are making a lot of money with pyroelectric detectors, and most of the detectors you see above the doors are made from these ceramic flakes. So the principle is that this ceramic piece, and actually I can show, let's say the principle. There is this ceramic little square millimeter of material, and heat comes in. There was no heat before, and then the heat changes, and that change in absorbed energy changes the temperature, and that temperature change displaces some charges, and those displaced charges cause a voltage to be measurable. And then that's the signal for the system to say, okay, open the door. If you wait long enough, those charges decay because the material is leaky. So one sure way not to be detected by a burglar alarm is to move very slowly. There are some movies that exploit that, or they heat up the room to body temperature. There was a movie when I was a postdoc. They heated the whole building to body temperature, and then they walked through the building freely because there was no change in temperature visible to the detector. Okay. And thermoelectric detectors, well, they exist as CMOS bolometric detectors as well. So what is the principle of all those? It's essentially that radiative power comes in, is absorbed in one substructure, and that substructure loses its absorbed energy by various paths that we have described. Of course, it is connected to some substrate by some material structures. So there is a thermal resistance, through material. So heat is partly conducted by solid materials, but heat is also conducted by gas conduction. That also corresponds to a thermal resistance. Now let me write this as gas and this as solid, and then I can also, the thermal radiation also corresponds to a thermal resistance, thermal radiation. So there are these parallel channels of heat loss, and whatever power comes in, the power heat is equal to G thermal of all the mechanisms times delta T. And that delta T is what we would like to measure in the sensor too, as a manifestation of the incoming power. So what is this GH, G thermal? Well, we've seen that it is equal to the sum of the G thermals, comma N. N equals 1 to, I don't know, maximum value. And this is equal to the sum of 1 over the R's, thermal, comma N. And so the overall thermal resistance is the sum of these inverse resistances to the power minus 1. It can be calculated if you know the individual contributions. And the value of this thermal resistance equals G thermal to the minus 1 will tell you how good your sensor can be, depending also on the quality of your delta T measurement. So this delta T measurement of the temperature measurement at the absorber and then at the reference temperature, that is the second essential part of the sensor. The thermal construction, and then secondly, the temperature measurement. And so if you look at thermoelectric radiation detectors, they look like these biflake pyroelectric detectors. There are usually two detector elements that are connected in a differential scheme. And if a person moves in this space from one side to the other, from here to here, then its radiation emitted, of course, in all directions of space, but also into this optics will be projected once on one element, and if it has moved on the other element. So as the person passes in front of this little seam detector, there will be little change of signals between the two flakes, and that is going to be detected as motion of a person. And so in the thermoelectric radiation detectors, this detection is done by absorption of thermal radiation. So you can imagine that this thermal radiation impinges on, well, detector element number 1 or detector element number 2, depending on whether the person is on the left or right. These detector elements here are thin membranes etched from the back of the silicon chip to produce a thin membrane made only of the dielectric materials of the CMOS process. And integrated in those thin membranes are little pieces of polysilicon and aluminum, or polysilicon of N-type and P-type, being integrated here, that constitute the temperature sensor. Because the thermal radiation coming in will produce a little temperature increase here in the middle of the structure with respect to the surrounding temperature T0 of the chip. And if you now have a differential system, again, you can detect whether one detector is slightly hotter than the other or vice versa, irrespective of the T0. It's not an absolute measurement. But these detectors, in comparison with the pyroelectric detectors, keep their signal. So if one of the two detector elements is at 0, and the other one is irradiated, the delta T will remain. It's not that some charges, decay or so through some leaky business. As long as power comes in, delta T will remain. That's the main advantage of thermoelectric detectors over bolometric detectors. To be stationary detectors, not only transient detectors. Now here you have two quite old chips, among the first that my PhD student at ETH Zurich produced in his thesis, René Lenkenhager. These chips are about 5 by 5 millimeters, so quite large chips. And they have also some circuitry integrated by a collaborating group from the electrical engineering department. So let me talk about some figures of merit. We have talked about figures of merit of magnetic sensors. Now we need, and also mechanical sensors. Now we need those for thermal sensors. So what people very often use as figure of merit is the responsivity, and it's written R. You can also call it S, sensitivity. It's the output signal per incoming radiation power, per absorbed radiation power. Volt per power or current per power, if the output of the system is a current. Then we have the noise equivalent power. So let me explain that in more detail with a graph. So 0, and here is time. So let's imagine that we have some power P1 impinging on that sensor, and then it produces an output voltage V, V1. And well, I'm measuring that as a function of time. If I come in with another power P2, I will obtain a second voltage V2. So the responsivity is actually the change of output voltage per input power, or delta V over delta P. I could also write. I don't have to write it differentially. The change of voltage per power. Now, I have drawn straight lines, or at least I tried to. In reality, the signal, the output signal will look like this. It's going to be a noisy voltage. And the same, this will also be a noisy voltage. And then there is a minimum amount of P change that I can still detect. So I have this value, and then say, I see the voltage, and I can know, did it change or did it not? And if I can detect that it changed, if the change, the level change is just as large as the noise is, then this is the noise, this corresponds to the noise equivalent power. So this delta P that goes in to produce this delta V, that is just detectable, that's just larger than the noise voltage, the amplitude of this noise signal, then this power is called the noise equivalent power. And interestingly, it is a spectral density. It is watt per square root hertz. It depends also on the bandwidth of the system. Then there is also the noise equivalent temperature difference that the sensor can detect. So if the environment changes by a little temperature change, will this produce an output voltage that I can still detect or not? The limit between non-detectable and detectable is called the noise equivalent temperature difference. And then people have also used another figure of merit, the D star, the detectivity, which is actually area, the square root of area per noise equivalent power. Now that's, you wonder, how can people do that? Why do they do that to us? So let me show you how noise depends on area. So if you have, so here is area, or I'll write square root area here. Yeah? And here is kind of the noise voltage. Yeah, noise voltage. Yeah? So we have a piece of detector, and you have some measurement, and you will notice that there is some typical voltage, noise voltage. So it fluctuates by some amplitude. If you now make that detector larger, so let me make it 4 times larger. What you will measure here is going to be the concurrent effect of the noises of the different elements. But if those elements produce statistically independent noise, like separate detectors, and you're just adding the signals of those, then somehow those noise voltages will be added, but they will be randomly added because these are random signals. And if they are uncorrelated, I shouldn't say uncorrelated, they are independent, then the effect will be that the overall noise upon scaling of the size by an area will grow like the square root of the area. So let's call this Vn0, and if you increase the size by some factor A, then the overall noise will be square root of A, not A times Vn0, because the noise voltage don't only add, sometimes they subtract from each other. These are random sinusoidal currents or sinusoidal voltages, and if you add them randomly, there is constructive and destructive interference. And the result of that addition, that random addition, is actually that the effective voltage scales at the square root of the area. And so square root of the area is a parameter, and we know that the noise voltage will increase with the square root of the area. So for one detector, you may have a curve like this. For another detector, you may have a curve like this. So this should go right through 0, 0. So, and then comes a guy and says, yeah, my detector has this noise. And I could also write here noise equivalent power. This noise equivalent power. And then comes another guy and says, yeah, my sensor is better because it has lower noise equivalent power. But then the first guy says, yes, but your detector is larger. I can do almost as good as you with a smaller one. And so this hick-hack, is resolved by the detectivity, because you can divide the noise equivalent power by the square root of the area, or vice versa. You can also calculate the square root of the area by the noise equivalent power, and then this number lets you compare all those curves on the same level. Then the guy who has a smaller detector can say, yes, but if my detector was as large as yours, my noise equivalent power would be really lower than yours. And so this is, it sounds like kindergarten, but sometimes it's a bit like that. And with the detectivity, you don't have these discussions. Okay, so that's and that also explains these funny units. Noise equivalent power is watt per square root hertz, and detectivity is square root of area, centimeter per inverse noise equivalent power, or per noise equivalent power times square root hertz divided by watt. And then what also occurs is, of course, the bandwidth is often equivalent written as B, and since we're talking of noise, I need to explain you a little bit about noise, in case you don't know already. So any resistor produces noise. If you have a resistor at temperature T, then and you do a measurement, let's think of this being, you know, not here, just a resistor, and then you do some voltage measurement like this. You may think that the outcome is zero because there is no current flowing through the system, but your voltage measurement is going to be unstable, not because the instrument is bad, but because charge carriers are moving back and forth in that resistor, and motion of carriers correspond to currents, and these currents are thermally driven currents by shaking atoms that push electrons back and forth, and that results in a voltage. This is a resistor's voltage. There is a noise voltage, and that noise voltage has a spectrum which is called the white noise spectrum, or Johnson noise spectrum. White noise. There are all frequencies are present with the same probability or the same contribution, and that contribution has been calculated. Now I'll show you in just in a second. Now resistors are always, you know, they're never alone. They always have an environment, and with respect to that environment, they always have some capacitive connection to the environment. So in addition to making such a measurement, this voltage, which corresponds to a voltage which can be written as an equivalent structure of an ideal resistor and then a voltage source producing that noise, we always have this C also connected in parallel. And if we now measure that voltage at that C, we obtain the noise voltage of an RC circuit, of a realistic RC circuit. And it's not going to be zero, it's going to be something because there's a VNR. So what is the noise power spectral density of a pure resistor? Let's assume that there is no C. That noise spectral density is given by this expression here. The average of V square per hertz is equal to 4 kBT times the resistance. KB is Boltzmann's constant. So this VNR is the noise spectrum, the root mean square noise voltage for a bandwidth of 1 hertz. If you have a filter attached here, so let's add a filter here with 1 hertz. This is the voltage, the average square of that measured voltage that you will get out. And if you now let that 1 hertz become 10 hertz or 100 hertz or 1000 hertz, you're adding noise contributions from different pieces of 1 hertz. And that noise is again independent. The noise at 1 hertz is independent of the noise contribution produced at 2 hertz and so on. And those contributions are going to add up again incoherently, which means that one can add the squares of the contributions. And so the outcome is that if I calculate now for a decent large delta F for some wideband frequency range, my voltage, that noise voltage, and I'm writing it with a capital R, is going to be this VNR, this little VNR for 1 hertz times delta F. And this is equal to 4 kBT R delta F. And this is actually a square here. So I need to add some explaining to this here. So this implies, and so the outcome VNR, the root mean square noise voltage measured from such a resistor over a bandwidth delta F is equal to this thermal contribution, this 4 kBTR times delta F with the square root. And if you evaluate this function. Of course, you have here the system-specific contributions. This is the same as here. And then you have a prefactor, which is 4 kBT. So at room temperature, at 300 Kelvin, this 0.13, and I should write here actually times 10 to the minus 9 nano. Yeah. So 0.13 nano, whatever SI value comes here. Yeah. So if you implement 1,000 hertz for a resistor, and you have a system that measures with 1 hertz bandwidth, then the outcome is going to be 4.07 nanovolt. So this is the noise voltage coming from 1,000 ohm resistor over a bandwidth of 1 hertz. If that bandwidth is 1,000 hertz, because you need to measure signals from 0 to 1,000 hertz, and fast phenomena are also important, like slow phenomena, then it's going to be multiplied by square root of 1,000, about 30. There will be 120 nanovolt. If it's a resistor of 1 ohm at 1 hertz, you have 0.17 nanovolt, 13 nanovolt. So these are some house numbers that I cannot forget anymore. Yeah? The 4 nanovolt per kilo ohm per square root hertz, for 1 hertz of bandwidth is something very fundamental. So this is the resistor as standalone. So if we have frequency here and we have V and R square, this is a constant curve. And the fact that this is constant for every 1 hertz piece, we have the same contribution, means, well, this is what is called white noise, independent of frequency. White, I think, is explained by the fact that if you mix all the colors, you get the color white. So if all the colors are mixed, then you get white. And so here, all the frequencies are mixed. Let's call it white. Nobody sees these voltage frequencies, but it's. And then if you now connect this resistor to a capacitor like this, and the capacitor is always there, then you have a system that equivalently could also be written as, so how did I write this voltage source, V and R, and now it is connected to a resistor, and then it is also connected to a capacitor. And we're measuring now this voltage here, and let's call this VNC, the voltage over the capacitor. What is that voltage? Well, this is a voltage divider with a resistive and a capacitive element. So it has a transfer function, and that transfer function lets us multiply the incoming source V and R with H, the transfer function. The transfer function is 1 over 1 plus I, the square root of -1 times 2 pi frequency RC. High frequencies go through easily, low frequencies get blocked. That's what this transfer function does. And now if I calculate V and C square, the absolute value of V and C, so it's really the absolute value that is squared here. Then I can just take the absolute value here, the absolute value of this exponent. Absolute value is equal to, or squared is equal to 1 over 1 plus 2 pi f RC square. And here's my f. And if I would like to know what is the sum of all the squared voltages, the integral of all the squared voltages over all frequencies, what I will do, I will integrate V and C as a function of frequency squared over all frequencies. And this is going to be VNR squared, which is 4 kBTR. And then comes the integral of 1 over 1 plus 2 pi FRC square integrated over all frequencies. And this integral here from 0 to infinity. And this is essentially for a wide band system that looks how much is the voltage of its output of the system over all frequencies, and out comes a number that can be calculated. And if I checked before the integral 1 plus x squared dx from 0 to infinity, that is equal to pi over, what was it? Pi over 2. I think that was it. And so you can use that input to calculate this integral here, and then some things will be dropped, some factor of 4, some pi's, some r's are going to be dropped, and at the end, maybe let me check what I'm saying. Here it is, pi over 2. Yes. And so if you calculate that, you'll see that the result is VNC is equal to KBT over C, square root thereof. So an RC circuit produces noise over the capacitor, and that noise integrated over all frequencies represents only information about the capacitor, the temperature and the capacitor. At the same time, if you look at the voltage drop at lower frequencies, you will obtain basically this flat portion of the spectrum, which later is dropped down by the action of the capacitor. But in this lower frequency range, it is constant, and that is given by these upper formulas. So the overall noise coming out of the system needs some knowledge about the capacitance and about the resistive part. And if we have only low frequency signals, then usually the capacitive thing doesn't matter at all. But it's good to know that. It's good to know that. For lower frequency signals, for instance, infrared sensors detect motion, and the relevant frequencies are hertz or 10 hertz. We're not producing high speed frequencies of thermal motion of hot objects. So then usually the upper part is essential, but there are other cases where this can be important. So let us look at some numbers. So I compared here pyroelectric with thermoelectric detectors. So commercial ones have sensitivities or responsivities of 4,000 volts per watt and detectivities of 10 to the 9 centimeter per square root hertz per watt. Whereas, let's say, optimized thermoelectric devices produce something like 500 volts per watt with a slightly lower detectivity of 3 times 10 to the 8, again with the same units, of course. So thermoelectric detectors are not as powerful as pyroelectric, optimized pyroelectric detectors, but they have this advantage of producing a stationary signal. So you have to trade off, to face the trade-off, what is better for your application. And linear arrays have been produced of identical elements, so they have the same performance numbers. And then when we talk about integrated systems, CMOS is of course better for integration with pixels that then are smaller, not as powerful, and so the sensitivity is decreased to something like 50 volts per watt, and the detectivity is also reduced to 10 to the 8 square centimeter per, well, the usual detectivity units. And in the arrays, yeah, bolometric 2D and CMOS thermoelectric, yeah, those numbers are even reduced further to 15 volts per watt. Bolometric is a bit better, 15 kilovolts, well, much better, kilovolts per watt. And then a noise equivalent temperature difference has been documented here with 0.4 Kelvin of detected temperature difference and 2 in the case of the thermoelectric devices. So one element of these thermoelectric devices is the thermocouple or thermopiles. Yeah, and I'll just briefly sketch what a thermopile is. It consists of two materials, a material A and a material B. And here we also have the material B. And the essential thing is that there is a temperature difference along two such materials. Yeah, so here, element A goes from temperature T0 to temperature T0 plus delta T. Yeah, and for sure, even if, well, if we had T0 here, T0, then material B would also go from T0 to T0 plus delta T. So we would have two materials exposed to the same temperature gradient. And if such a situation is occurring, then we are able to measure a thermoelectric voltage at the output. And that thermoelectric voltage is equal to this temperature difference, common to A and B, times the relative thermal power, the relative Seebeck coefficient, which is tabulated. It can be some hundreds of microvolt per Kelvin of temperature difference. I also noted here T1, yeah. So the measurement is done at another temperature than the two temperatures to which A is exposed. So just to make this easier, let me, in this case, write down that at some point, this element B also has temperature T0. And then you have, again, a complete thermocouple between here and here. A and B go from T0 to delta T. And what happens here in material B from T0 to T1 and here from T1 to T0 doesn't play a role, because it's the same material exposed to the same temperature difference, and it produces a thermoelectric voltage that just cancels. So it doesn't play a role. We can put any temperature here, fortunately. And so in reality, these materials are, so I have blue and green here. Yeah? So let me show you that in this structure, material blue comes in here as aluminum, yeah, buried between dielectric layers, so we don't see it here. The same here, yeah? Buried below. And then it has its contact to green. Yeah? And the green we don't see either because it's also buried. Yeah? So here we have two such thermal elements, like the ones I circled in black. So this corresponds to the black encircled area here. Yeah? Where here at the front we have T0 plus delta T, and in the back we have T0. So if the front is hotter than the back, there will be a thermoelectric voltage measurable between this location and that location. And if I continue now this green by some additional blue and this by some additional blue, and then here I do my thermoelectric voltage measurement, TE, not thermoelectric, TE, thermoelectric, then I will obtain that signal as in this schematic circuit. And if I'm now hooking up two elements and then I'm measuring my voltage of the two elements, I'm obtaining, of course, the sum of the two outputs, voltage plus voltage. Yeah. Therefore, if you have a thermal pile, yeah, which is a series arrangement of n thermocouples, then the voltage of the thermopile Tp will be n times the thermoelectric voltage of the individual thermocouple, which is alpha delta T. And so here you have an example of a thermopile, of a simple two-leg thermopile made of aluminum and polysilicon. Here you have another one, which is P plus silicon and aluminum in a suspended structure. Here you have poly of one kind and poly of another kind, N and P poly, that are connected here, you know, so you have blue, let me say blue and green embedded in these dielectric sandwiches. And then you have a little connection here that I'll draw in orange. Yeah, I could just make here an orange connection between blue and green. Why is there an orange connection? It's made of aluminum, because if you connect P poly to N poly, you produce a diode. And then at the back, the diode goes back from N to P, and then that's another diode which is connected the other way around. And so you have a situation with back-to-back diodes that doesn't allow any current to flow. Yeah? So in order to prevent that, one does the connection by aluminum, yeah, a metallic contact to silicon. Yeah, so an ohmic contact, and then, oh, that was the wrong color, green again, and then you have the ability for some signals to propagate, for some currents to flow if needed. Yeah. And here is another, some P plus leg under the silicon oxide sandwich, and then some polysilicon within, N polysilicon within the dielectric sandwich. So this is a very schematic way of how to produce, and you see that in order to produce these thermally well insulated structures, you need to under-etch them. Yeah? So then under some external radiation, yeah, this delta T can really be produced. If the silicon was still there, that heat would be eliminated very efficiently into the substrate. You wouldn't get any delta T. By insulating the structure, the heat absorbed needs to flow along the structure. There's a large thermal resistance, and therefore there can be large delta T. So when you look at thermocouple materials, it turns out that semiconductors are quite reasonable structures, because the figure of merit that describes their efficacy as thermoelectric converters is alpha square, the Seebeck coefficient square, multiplied by the conductivity divided by the thermal conductivity, or if you want to write it like this, it's alpha square divided by the product of the thermal conductivity by the electrical resistivity. And that value reaches a peak for semiconducting materials with high free carrier concentrations. So actually, in this later, latter part of the concentration, actually these bismuth telluride and other materials that were mentioned earlier, where were they mentioned? Telluride. I thought I'd seen such, yeah, here, yeah. So this system of materials is actually ideally placed in this diagram. The semiconductors we usually have in our systems are more on that slope, so it's not super ideal. But how does this Z become peaky here? It's because the conductivity increases with numbers of charge carriers, of course. The Seebeck coefficient decreases, and the thermal conductivity increases. So it's this combined effect of all these objects here, these quantities that produce a curve that peaks at some intermediate carrier concentration. Yeah, so to finish, let me just show you an example of a thermoelectric detector of the array type that has been produced again by Nikolaus Schneeberger, whose PhD thesis that was 16 by 16 detector array. What you see are little detector elements, S-shaped detector elements that are suspended between one side at T0 and another side at T0. Maybe I can write that in another color, black, T0. And then by the absorption of heat, its center is increased to T0 plus delta T. And so if there is a thermal scene being projected on this array, of course, each pixel will receive different amounts of power, and therefore the delta T of these different pixels will be different. And then you can read out the signal. And that signal is produced by thermoelectric elements, by thermopiles. So you see these lines coming in here. This is like an aluminum line, and then there's a polysilicon below, and then it's connected to the next aluminum line, and then it goes back as polysilicon again. And there are, I think, 4 such elements in series, back and forth, back and forth, back and forth, between temperature T0 plus delta T and T0. I'll remind you later. And there are 4 on one side and 4 on the other side, and the sum of those thermoelectric voltages is then the output signal of this pixel. And there is also some piece of circuitry that allows to change, to amplify and filter that signal. The structure is produced by anisotropic etching. You see that the silicon is removed below. It's an EDP etching because it's from the front. This is the only etching that really does that etching reliably. And you see also the structure is compatible with the under etching because you have these convex corners that allow the structure to be under etched from all sides. So that under a series of such pixels, there is now a big groove of removed silicon, and the pixels are suspended over that groove. That has taken a while, but after the under etching was completed, the remaining structure is then, of course, just this groove with walls made of one silicon. And there are many such grooves here along this direction here, separated by some ridges of silicon between the grooves on which lines can be supported and that are thermally well connected to the rest of the chip, so that the temperature T0 of the chip really is present here at these suspensions. Okay, I'll stop at this picture here, and then we'll see another example of thermoelectric sensor next week. And I think we will finish that chapter next week because we have exactly reached half of it here. So with that, I would like to thank you, and I'm looking forward to seeing you next week. Bye.